We spent the first video in this lecture doing math, and now we come to what I think is one of the most important points in the whole study of classical thermodynamics, a point where it really all starts to come together. We're going to talk today about free energies and the way that they arise as a result of the Legendre transform. All right, so you now know what the Legendre transform is, just in general, for real functions of a single variable. And that's a little strange in the sense that all of the variables that we've been dealing with, all of the functions, are functions on a state space. And so they're usually functions of many variables. But that's all right. Let's just define a function of a single variable in the following way. Let's say that we're working with a gas system, getting a little bit ahead of myself here. So gas system with variables U, V, N as internal energy work coordinates on the state space. Okay, and now we know that we have the freedom to choose whatever coordinates we want, and in particular, we could choose the coordinate system SVN, and we could look at U as a function of SVN. So in coordinates SVN, U is a function of SVN. Now, I want to define a particular function A, which is defined in terms of U, but is now a function of a single variable. So let's just say A is equal to, and I'm getting ahead of myself again, A sub Vn of S is equal to U of SVn by definition. Now we have a function of a single variable, and we can take the Legendre transform. So let's do it. A bar sub Vn of a variable. We need to come up with a name for the conjugate variable, and let's go with, I don't know, little t is going to be equal to the maximum over S of, well, we get U minus little t times S. Good. Okay, how do we find a maximum like this? Well, we showed in the last video, and I'm sure you're very familiar, we usually just use calculus and take a derivative. All right, so let's take a derivative of this with respect to S and then set it equal to 0. So S star is defined by du ds evaluated at S star minus little t is equal to 0. Okay, and moving this to the other side, we see du ds evaluated at S star is equal to t. Now, I'm going to be clear here that because u was really a function of all of these variables, this is a partial derivative fixing v and n. In other words, fixing all the work coordinates. And that's equal to little t. But by one of the partial derivative identities we've shown, this is true if and only if ds partial s partial u is equal to 1 over t. But look at that. What we've done is reinvented the temperature. And that's somewhat astounding. So let's write what we've figured out. Temperature is the natural Legendre conjugate of entropy under this change. Now, I've called this function a bar, and I've said that it's only a function of t, but I could have left it sort of as a function of Vn and t, and why not? Typically, that quantity is given the name f, and I will say of tvn. And that quantity is equal to u minus ts. Now, really, I should be putting u minus ts star. But since I'm thinking about all of these things as functions on the state space, and here s star depends on t in some prescribed way, we're actually totally fine just writing this. This is well defined and it makes sense. So now we have some other quantity, and notice that it has units, or it has type energy. We have u here and then t times s. S has units kb, or has the same units as kb. And then anything with units of kbt has units of energy. So look, we have an energy here. This object is therefore typically called the Helmholtz free energy. Okay, wonderful. But there's no reason that we had to pick S as the coordinate to transform. Notice that exactly the same thing could have been done with V or with N. And in each case, we would have gotten a slightly different expression. Now for V, we do need to make one small change, which is to define the Legendre transform with a plus sign here, because again, we have this ambiguity where pressure is really kind of the negative of what it ought to be. So let's go ahead and try that. Let's define U minus or plus PV to be called H. And let's define U minus TS plus mu N to be called G. Now, the thing that we naturally want to check is that we get something like this again, that these intensive quantities are also naturally Legendre conjugates. I don't want to do this for all of these, but let's at least do it for H. So in this case, we have that H, and let me preemptively say of P is equal to the, well, I guess it should be the min now over V of U plus PV. Again, this is all because of the weird opposite sign relationship here. Okay, and then we just do the exact same thing as we've done before. So now we know that partial U, partial, in this case, V, while fixing, well, now this is a function of S, V, and N again. So we're fixing S and N is equal to minus P. Okay, so now how can we get from here to something that we can more easily work with? And the answer is that we need to use the triple product identity. Recall that that's going to say that dx dy fixing z, dy dz fixing x, dz dx fixing y, all of that is equal to minus 1. So then what we would need to do is multiply some of these over to the other side. So in particular, this all implies, for instance, dx dy, and I should be saying partial, is equal to, if we move this over to the other side and flip it, it becomes partial z partial y fixing x. And then this one becomes partial x partial z fixing y. And I've forgotten a minus sign. which I should probably put back in. Good. So let's apply this up here. And what do we get? So here, n is going to be fixed through everything, so we're just going to ignore it. But s is going to be serving the same role as z, u as x, and v as y. So again, s is z, so we get partial s up here. Y is v, so this is partial v. I'll put my minus sign out here just so I don't forget it. And then we're fixing u, then partial u, partial z. Z again is s, fixing v, and both of these will also fix n. Notice that the minus signs cancel out. Okay, so we're almost home free here. Check it out. This is ds dv fixing u and n. Nothing has to change. But then du ds fixing the work coordinates is exactly t. And this is equal to p. That fits exactly the definition that we used and introduced back all the way in lecture 5. So here we go. We're basically in a good place. The intensive coordinates that we found as these derivatives of the entropy function of the equation of state are in fact also, you can also think of them as Legendre conjugates to the work coordinates to which they correspond. We would find the exact same relationship if we took any generalized pressure and any generalized volume. This means the Legendre transformed energies, these free energies, are in fact very powerful tools. Before we go, let me just give a quick name to these two energies. This one is called the enthalpy, and this one is called the Gibbs free energy. Okay, actually, I'm going to clean up the board and we have a bit more to do. Okay, we're back, and I have gotten all of the thermodynamic potentials or free energies, thermodynamic potentials being another name for them, back up on the board. Now it's time to look at a consequence of the way that we've defined these. And what we're going to do is use the first law of thermodynamics to make a little bit more sense of these in infinitesimal form. So let me take each one of these, and I'm going to act on it by the exterior derivative. So first we get df, which apparently is equal to du, and then we'll need to use the Leibniz rule on the second term. So we'll get minus s dt minus t ds. Now before I go on to those others, let me use the first law of thermodynamics to expand this du. So du, we know, is equal to t ds minus p dv plus mu dn. And this is just really the sum of the work variables if we're dealing with a more general system. But let's stick with gas systems for now. So now if I pull down this equal sign, and then I bring down these two terms, minus s dt minus t ds, I see that we have a cancellation. This TDS cancels with this TDS. In the end, we get this is equal to minus s dt minus p dv plus mu dn. Good. Let's do the same thing for the enthalpy. So dH is equal to du, again with the Leibniz rule, plus v dp plus p dv. And once again, the minus pdv in du cancels with the plus pdv that we've introduced. So when the dust settles, we're going to get that this is equal to tds plus V dP plus mu dN. Last up, for the Gibbs free energy, we have the following. So now we're going to get du minus s dt minus t ds plus v dp plus p dv. And we'll find that parts of du cancel with both our TDS and our PdV. So that when the dust settles in this case, we get minus SDT plus VDP plus mu dN. Now, all of this leads to the notion of natural coordinates. Each of these thermodynamic potentials has a set of natural coordinates. This actually would have already been clear simply from the fact that these are Legendre transforms. So we want to typically use Legendre conjugate variables where we've actually done the Legendre transform on one of the variables. But this is a clear way to see it as well. The natural coordinates for F are going to be T, V, and N. In other words, the coordinates that now have these one forms attached to them. The natural coordinates for H will be S, P, and N. And the natural coordinates for G will be T, P, and N. So what does it mean that these are natural coordinates? Well, in a word, it means that if we wanted to figure out the changes in some quantities and we knew the changes in the free energies, it would be easiest to use the free energy corresponding to the coordinate system that's the natural one for this. So for instance, if we had a transformation which fixed V and N and changed T, and we knew the changes in the free energies, then it would be very natural to use the Helmholtz free energy. Similarly, if we had a coordinate transformation, or sorry, some sort of operation on the state space that fixed P and T but changed N, then the Gibbs free energy would be very natural. That leads us to one final point before we end our work here today, which is to talk about the Gibbs free energy. Now, I want to note that the Gibbs free energy is a function, again, of T, P, and N. It's also extensive. If we look over here, U is extensive, S is extensive, and V is extensive. And so G must also be extensive. In fact, all of the thermodynamic free energies are extensive. But if G is going to be extensive, and it's a function of two intensive variables and one extensive variable, then we've already shown that the only way for this to be true is if it is some function of these variables times n. So let me establish a new column here and we'll show that. So G of T, P, N is equal to some function f of T and P times n. But now let's think about what that means for mu, which is the derivative while fixing T and P of G. It means that mu is exactly equal to f of TP. Good, but then look, we just substitute mu back in. Since this was a linear function, this all makes sense. And we find that G is exactly equal to mu times n. Now, the only thing that's special about G here is that it has exactly one extensive natural coordinate. So this would always apply in one of those cases. And this formula is very powerful, as we'll see a little bit later in the course. That's all I wanted to do for now. I'll see you in the next video, and thank you so much for watching. Bye-bye.